Hello, everybody. So today we're going to talk about monads. You may learn something about them. So functional programming is about composition. What we want to be able to do is take our little bits of things that work and put them together into bigger things that work. And over the last couple lectures from this series, we talked about the Functor type class, which gave us a way to apply functions to data in context, and we talked about the applicative type class, which lets us apply functions in context to data in context. And those two new ways to apply functions gave us new ways to compose our programs together. So today we're going to talk about a third type class called Monad, which again gives us a new way to apply functions. In this case, functions that take a pure input and produce a value or choose a value in context, and they give us a new way to compose things together. So we can make we'll see how to make like context-sensitive parsers or functions that, or programs that can fail based on a pure input. So let's do a little bit of review. Functors, you probably remember the definition. We have one type class method called fmap, and I'm going to keep referring to the f in functor or applicative as the context of some data. So it lets us apply some function from A to B to a value with type A in context, and get a result out also in context. So there's some examples that you've probably been over before. We can use the maybe instance of Functor, and we can try to parse a value. And if it successfully parses as a number, then we can apply some function to it. If it doesn't, we apply the function, we still get back a result of nothing, which in this case means that we failed to parse. Another example is the list monad, where you probably read that fmap is the same as map, so our context is we have multiple values, and we want to apply a function to all of the values, and we get back multiple values. So it's the same as map. Applicative functors, we did in fact, Sean did in the last couple lectures. So we have two type class methods now. We have pure, which lets us take some pure value and put it into a default context. And then we have the Anglebum or starship operator, which lets us take a function that's in context and apply it to a value in context. And remember that we were motivated by trying to add two numbers that we parsed. So if we had successfully parsed both, then we could apply the function to combine them, in this case addition, but we couldn't do it if we did not. So this was if we only had functor, right? Because we had no way to get a function in context to use a partially applied function there. So again, we have two examples. This is the function we were trying to write last time, which is we parse two values and we combine them with some binary operator. And with lists, it's in this case we get the Cartesian product. So we're going to take two sets of multiple values and combine them together with multiplication. We get the pointwise multiplication of each one. All right. So if you recall, if you did the homework exercises, maybe at Hack Night, the homeworks for the previous lectures talked about this parser data type. And a parser we've defined as basically a function that takes in some input string and it returns a result. And the result could be either a successful parse, in which case it contains the value we parsed and any remaining input, or it could be a failed parse, in which case we get nothing. And recall that we defined functor for our parser data type. So once we had parsed values, we could operate on them if they had successfully parsed. And we also defined an applicative instance. In this case, we can read in two values and combine them together. I keep using multiplication because I'm not very creative with examples. But in this case, we can define a new parser that consumes two characters from the input, combines them in some way, and we get out a single value. And the important thing to note is because we have these type classes that have laws, right? If we combine things together with fmap, we're going to get something that behaves like our original data type. Or here we have our combined parser P, which if we've implemented the applicative instance correctly, is still going to be an applicative. We won't be able to tell it apart from some primitive parser that we defined. Making sense so far? I can't tell the difference. Very confused. Okay, so that's very useful, but there are things that we can't do with applicative and functor. So one is use our parser to parse things in context. Let's say we want to, the common situation is we want to read like a delimiter or a length description and then read that amount of input, right? And we need to turn that, so we need to chunk out our messages here that start with the number of characters we need to parse, and then we need to read that number of characters. So we have these two primitive functions that I think we did for the homework. We can parse in a number, or we can parse in, some letter, any character, or any alphanumeric character. But how do we combine them? Well, if we have an int, we can parse a list, right? We can use applicative for that. We can use recursion to define this. So all we do is we use cons, and every time we parse a single letter, we cons it onto the result and put those together with the Angleball operator. So we can define this function, that's fine. But what happens if we get the int from our message, or from our input string, right? We need some way to apply parse n to an integer in context, in the parser context. Which means if we've successfully parsed a number, right, we should use that number to determine how many characters we need to read in. If we haven't successfully parsed it with nothing, we need to just pass that nothing along. We need to fail to parse. So we can tell what type this has to have, right? We can just combine these together. We can parse int and then parse n with that int. But we can't use applicative to combine these, right? Because we have an int in context. We parsed it. Another example is you might want to implement the Unix cat function. I'm assuming most of you are familiar with it, but we give it a file name and it reads in the file and spits it out to standard out. So we have these functions that are defined for us by the standard library. We have a read file function where we give it a path to our file and it gives us back some string in the I/O context. We performed I/O. And we also have hputster, which lets us write some data to a file handle. In this case, we'll use standard output. So we have a similar sort of structure going on here, where we can say, okay, we know how to read in a string and get a string in context. And we know how to write a pure string out to the file handle. But how do we combine them? Right? Because we have a string in context and a function that takes a pure string. So I'm going to take a short detour. So far, we've talked about several different ways to apply functions to values, right? When you first begin learning Haskell, you learn about the dollar operator, which is essentially the same as ordinary function application. Right? We take a pure function from A to B, we apply it to a value with type A, and we get back a value with type B. So then for Functor, we have fmap, which lets us apply a pure function to a value in context, and Angleball. I need another name for that. That lets us apply a function in context to a value in context, right? So we got this table. You can see we're adding context in different places. We already worked out sort of what shape we need for our new way to apply a function. This is what we're looking for. So we got fa, and we have a function from a pure input to a value in context f, and then we need to combine those to get just one value in one context, right? Same pattern for both of these things. So you've probably guessed by now that this is what monad gives us. So there's a type class in control.monad, which is defined like this. Any applicative any monad is also an applicative. So applicative is the superclass of monad, just like Functor was a superclass of applicative. And we have two methods. Return behaves like pure. So it lets us take some data, some pure data, and insert it into a default context. The context, of course, depends on which instance we're using. And then we have this greater than equal operator, which is pronounced bind. I think it's meant to somehow convey that you're taking something from one side and giving it to the other side, but I don't really know why it looks like that, but it's pronounced bind. And that's exactly the signature we were looking for, right? So if we look back at our table, pretty similar to applicative, but now we can take in a pure value. Yeah, that's too far away. We can take in a pure value, and we take a function that takes a pure value and produces or chooses some context and apply it to a value in that context. So these are some examples of functions. We've seen some of them already that behave like this. So parsing type functions where we may fail to parse, or multiple value output functions or non-deterministic functions where we take in some value and return multiple values. I/O is also an instance of monad. We'll talk a little bit about that later. So parse n is also the same shape, and it turns out, yes, we can write a monad instance for parser. But it's the homework, so I'm not going to show you. So instead, we'll talk about some other monad instances to get started. So maybe, which I've written here is a monad for failures, but it's not just for failures. It's anything where you have some singular value that you may return. But maybe is a monad. So for return, we need to insert some value into default context, right? We can use just, has that same type signature, right? A to maybe A. And for implementing bind, it's pretty simple. If we have a failure value or a nothing value, and we need to apply some function to it, it's straightforward. We just apply nothing, or we just return nothing. In fact, there's nothing else we can return, right? We have no value that we could give it. So there's no choice what to do for that case. If we have just, and then some value, it's also pretty straightforward. We simply apply the function to the pure value, and the function itself will produce a new context, either nothing if it fails or just if it's, again, succeeded. So using this instance, we can define a couple functions here, right? We say like save half. Oh, I forgot to change that to less than or equal to. So save half says if we've got an even number, we can divide it, of course, but if we have an odd number, that doesn't make sense, so we'll have to fail. Check natural, or should be check positive, I guess, or check greater than 0. Just ensures that we have a positive value. If we encounter a negative value, we'll fail. And safe divide prevents divide by 0 errors in the same way. So if we've got these functions, we can use the monad instance and combine them together, right? So if we chain several of them along and we pass in 30, well, it's okay. We can divide it by 2. And that's 15, which is still greater than 0, so no problem. And if we divide 45 by it, we'll still get back 3. So no problems, no divide by zeros, right? We get back a value in context, and we can compose these together. And just some more examples here. Depending on what input we get, the success or failure at an earlier stage will be propagated along, right? So bind lets us compose these things together. So for comparison, I've written this, kind of a combo function from the top here. If we didn't have the monad instance, right, how would we implement it? Well, we have to check every time we apply a function to get back a value. Could have failed, could have succeeded. If it fails, we have to return nothing. If it succeeds, we have to manually apply it, right? But it's very difficult to extend this function. We have to write another function that wraps around it that does the same case thing, right? We don't like boilerplate, so we can get rid of it by defining the monad instance, which does this for us. And it's much easier to write just using bind. I'll go over this one quickly, but we also have a monad instance for lists that may be a different way for you to look at it. So in this case, return, we have to default insert like a single value into some default context. Well, again, we only have the one value, so we just have to put it into a list and give that back. It's the singleton function. This is the way the bind is defined in control.monad. Now that we think about it like this, where we have multiple values, and we need to apply a function from one value to multiple values to each of those. So we map that function across, and now we have a list of lists, but we need to return a value in a single, or set of values in a single context, so we need to flatten those lists with concat. And I've sort of defined some silly functions here that let us go up to some integer or give us the range between some integers by counting. And we can combine them together, and right, so it's you can see sort of what composition does here, which is we're sequencing the two functions together. I don't know why you would want to really generate this table, maybe for Project Rover or something, but there's an example of, you might do something that produces multiple values and compose them together. So again, I'm not going to give the instance for Monad because it's the homework, and I think it's a really good exercise. But assuming we've done the homework correctly, we have an instance of Monad for the parser type, and we can now we can build the message parsing function that we wanted, right? So we can use bind to put together parseIn and parseInt. It's very straightforward, and now we can successfully pull messages out of our string, right? So context-sensitive parsing. Hooray! There's two other instances I want to mention. There's many instances, of course, in different libraries around, but I just want to point out that the either type, which you're probably familiar with, you can define a monad instance, but what's interesting here is that either takes two type arguments, right? It's written as either A, B when it's defined. And anything you make an instance of monad can only take one type argument, right? Like list or maybe. So the trouble here is that we need to fix the left hand, or like the error type in the either if we define a monad instance for it. What this means practically is that if you have one function that could, return a successful write some value, and then the left with, an HTTP error code, and another function that could return a successful value, or its failure is like a Unix error code, you can't compose them together because the E is a different type. Does that make sense? And then I/O is also an instance of monad. The implementation is hidden from you. But using this instance, it's very easy to write a path or a cat. We can simply put our two functions from before together with bind. And I've just written below here another example of where you might want to do something sort of context sensitive in an I/O situation where you can use this getArgs function from system.environment to read in the command line arguments to your program. And then depending on what those arguments are, you may do something different. You may exit with a failure immediately or go on to perform some other processing if you've gotten, in this case, I guess we're processing some file input. Okay, so it's a type class, and it's a very well-behaved one. It has some nice laws that go with it. There's 3 laws for the monad type class. The first one is pretty easy. It's the same as for the applicative type class. So we say return behaves like pure. If you, I'm going to say this right, if you return a value into a default context and apply a function to it using bind, it's the same as if you had simply applied the function to the pure value without any monad involved. The next law says that return is an identity, which means that if we use return as the function to apply to a pure value using bind, we'll just get back the same value. And the last law is that bind behaves associatively, which means it doesn't matter which function application we do first as long as they're in the same order. But that's a little unclear, so it's easier to understand these laws if we define this kind of fish operator. If you compare with the function composition operator from the prelude, you can see that the shape is pretty similar. The fish operator basically gives us function composition for functions that take in a pure value and produce some value in context, right? And if we use this fish operator to look at the laws, it's a lot easier. We just say, well, return is a left and a right identity for composition of this type of function. And associativity is much easier to understand. It doesn't matter which value we generate first and feed to the other function.
Should there be a return on that top law, or am I crazy?
On the which?
On the top law, like law number 1.
Should it be a return? It is a return?
I mean on the right-hand side.
Where are you looking? Right at the top.
So here? This kind of guy?
Yeah. So should it be return KA over there?
No, if you look at the type, right, K is maybe something that takes in a pure value and gives back, let's say, a maybe, right? And return is going to have the same shape. And so if we apply here, right, we get a maybe something, and we apply K to it. And here, we apply K to the pure value. Either way, we're going to get a value in context out. Okay, let's see. Oh, right. So the monad type class has another method, which is greater than. It's pronounced then or and then. And all it is for combining two actions together where you don't care about the value. What this means is we compose two things together, and we only care about the context that it happens in. So in the parsing situation, we might want to check that something has succeeded, but we don't actually care what the successful value is. We just need to do something different depending on whether it's successfully parsed or failed. And the definition is part of the type class, and it's given by, in terms of bind. We just apply it to some function and ignore the argument. Oh, yes, and so you may recognize this if you've been playing with applicative a little bit. Applicative defines this sort of, I forget what the name is for this, but it's like two sides of the Engelbaum operator, and it's essentially the same thing in different orders. So it's where we care about propagating, our context without the value. Skip, that's what it's called, I think. Okay, so Haskell's been using monads to do various useful things for a long time, or Haskell programmers have been using them for a long time. And they're so common that there's syntactic sugar for it. So you've almost certainly used do notation before, but I've just given an example in case you're still a little shaky. We can take our parse message function from earlier, where we just need to combine parsing an int, and then passing that to some parser that will consume a number of characters. So if I introduce this n variable, we can see that, I'm going to tell you that these are the same thing. So the do notation, instead of having to explicitly write the lambda and then the bind operator to apply the function to some value, we can instead just create the same binding with the left arrow, and we don't have to do any sort of line termination. So just for the sake of more examples, I've rewritten some of the functions from earlier using do notation. In the first case, of course, it's a little longer and maybe harder to understand, but same thing's going on, right? We ensure that we can divide by 2. If we have successfully, if we've been given an even number, then half will be half of that. We can apply check natural, get back a natural number, and perform our safe division. And of course, if at any point this fails, if we give it 17, we can't divide by 2, this whole thing is kind of null and void, as it would be if you compose them together with bind, right? If this fails, you don't care what's over here, you're just going to return nothing. And then we have an example from IO, which is kind of the same, just showing that you can sort of, you can nest do's. So if you need to perform several actions in sequence, and compose them together with bind, you can nest these. You can have as many do blocks going to the right as you like. So I just have one more example, which is a little bit more general. So the first line here, you should go over here. You guys are probably getting one. The first line here is the thing you've seen before, right? We just simply bind a value or a new name by applying our function. The second line, I want to point out that you can pattern match within do notation. So here we return a tuple, and we can do the same thing as if we were writing a function definition and pull out the 2 values. If we want to combine if we want to compose 2 of these functions together using the and then operator, remember that this bind to a lambda where we ignore the argument is the same as and then we don't have to create a new name with the left arrow at all. We can simply write the action in order. For some reason, if you use let within a do block, you don't need to say in after it. And the last line is the same in both cases. You can also write do notation with braces and semicolons if you really want, or if you're at the interpreter and you're trying to make it all fit on one line. Can't tell if anyone's really confused, but if you are, please speak up. Okay, so Monad is not just a type class. As I mentioned before, it's used for all kinds of different things in the Haskell programming language, and it's used for so many things that we have a bunch of standard tools in control.monad that work for any monad. And they sort of encapsulate patterns of composition that people find themselves using often. So the first example I've written up here is the sequence function. So we take a list of values in context, and we need to put them in order and get back a list of values, comma, in context. Right? And the implementation is very simple. It's recursive, and we use do notation. So we match on the first element of the list, we apply it, using this left arrow, we get the pure value from the context. We then recurse, call it on the rest of the list, and get back the remainder of our results. And then you can just use return, which often comes at the end of a do block if you've computed some pure value to put it back in context and to do that. And so in this case, what we're doing here is we're building the list as if it was a pure list, but we're using the monad instance for whatever monad we happen to have, to make sure that the actions happen in context, in the order they're given in the list. Other functions include the sequence underscore, where we want to, it's just like and then. We want to take a list of values and put them together in order, but we don't actually care what the return value is, we only care about the context. Forever lets you take some action and run it forever. Join is an interesting one. If you have 2 layers of context, it turns out that for any monad, you have a way to put them back into a single layer. So for the list monad, remember we talked about how we need to, we apply a function that generates multiple values for each value in the list, and we need to combine them together again with concat. Well, for the list monad, join is the same as concat. And so you can also think of join as being somehow the inverse of return, where join lets us flatten a level of context, and return lets us add a level of context, a layer of context. The when function lets us test whether we have some Boolean value. If it's true, we want to perform the action. If it's not, don't do anything, just move on. And there's a whole bunch more functions in control.monad, mapm, form, filterm, foldm. I really encourage you to open up the documentation and/or the source for that module and read through it, because it's extremely interesting. One more tool is replicate m. So the definition is very simple. We replicate some action several times and then apply sequence to put them in order. Right? Using replicate m, we can simplify our parser from before. So rather than having to use explicit recursion to define parse n, we can just use this combinator, and it's very short. And we can use it again here to get multiple messages out of our input string. All right, so I lied. Control.monad doesn't look like I said before. One difference is that they use the letter M everywhere in control.monad. I used F for consistency with Functor and applicative. So there's a couple other things you'll notice here. There is no superclass of applicative. So as defined in the standard library now, you can have a monad that's not an applicative. This is because people understood how to use monads to do these kinds of compositions before anybody had come up with the idea of an applicative functor. Unfortunately, this is going away in like a month or 2. So the next version of the GHC compiler will have the correct superclass with it. Another interesting historical tidbit, return is the same as pure. So if we had known about applicative functors when people had defined the class monad, probably wouldn't have had any return, it would just say pure. And fail is another method in monad. It's self-describing, and you should not use it. Okay, another accident, maybe. So look at the definition of my function here, right? We perform 2 actions, get out 2 different values, and combine them with some other function that produces context. But we don't actually need a monad instance for this. We can write the same thing with applicative. So the interesting thing here is that if you do write the function in this notation, the compiler will be unable to tell that you only need applicative. Because when it converts the do notation into actual code, it removes the syntactic sugar, it implements it in terms of bind and return. So this is something to be aware of if you're trying to decide how to write something. If you don't need a monad instance, of course you shouldn't require it. And if you use do notation to write your function, the compiler will require it for you. One more accident. So we have these nice tools here, and we've generalized over all our input and output types, and we've generalized over our monad, and we're using lists, and you can only use lists. This is kind of a bummer, but fortunately there is a solution. There are 2 modules called data.foldable and data.traversable, and they define classes with the same name as the module, which give you slightly different ways to work with values in context or in a collection. And in this case, for almost all these cases, I think we have equivalent combinators from control.monad, but they're defined in terms of anything that can be a traversable or foldable collection. And if you're curious about these, I encourage you to ask Tony about them afterwards. Okay, so that's all I have. Quick recap, we talked about bind. It gives us a new way to apply functions. We can apply a function from a pure input that creates a value in context to a value that's already in that context. The monad laws, as with functor and applicative, let us use this composition function to build new programs. And if we've written our monad instance correctly, then our new programs will behave exactly as if we had written them by hand to do all of our error checking manually or whatever. But of course with a lot less boilerplate. And the only other thing I'll add is the standard disclaimer that if you don't need monad, if you can get away with applicative or functor, you should get away with less, because it will be easier for other people to use your code after if they don't need to provide a monad instance for whatever your function is going to operate on. Yep, the slides are up. Questions? That's really good or bad.
Do you know whether the GHC 710 monad class has a default implementation for return based on pure?
I do not. Anybody? No, I don't know.
Sure. That's a good question.
Thanks.
With the do notation and applicatives, there is an extension, and I don't know if it's in 7.10 or 7.8.
It's not in 7.8.
It's not in
I
7.8.
meant to mention that, and I totally forgot.
I'll go for it. Is there a way that we can...
Basically, there's just a language extension, I think, in the next version that fixes the applicative and monad thing, that also, if you turn on the language extension, will desugar that properly and only require an applicative instance.
Is that fully ready?
I think the extension is coming in, but it doesn't. I'm not sure you get it on do notation. I think it's adu, so you need to have a different.
Oh, is it?
Yeah,
Last time
because
I-
the program changed.
Right.
Yeah, I guess, yeah. Okay, well,
Like you have to be aware that that's what you want.
Right. Okay. So we'll at least get do notation-ish syntax for working with the applicatives, which is cool.
Much I do.
Sorry. There's about 8 people in the room who are thinking about the same joke. Yeah. Well done.
Yeah, I got a question. Like,
Yeah.
How do I know when I need an applicative and when I need a monad? Like between the two of them, how do I know when I've stuffed up and I've used the monad when I should just the applicative?
well, I don't know if there's a general way you can simply. Actually, well,
Yeah, if you go back to that do notation, you'll see that it's not context sensitive,
yeah.
right?
So I mean, you can examine it, right? And if you can figure out, if you can figure out how to write it only with an applicative instance, then of course, which one do you want?
I don't know, I remember it popped.
Oh, the one for.
So that one's context sensitive, right?
Yeah, no.
I think there was one before that though.
No, it's after that. It's the one.
There it is.
Yeah.
So see how the X and the Y, or the X is not used on the right side. So it's like do then X and then X is not used.
Yeah.
So since X is not used, in other words, it's context insensitive, we can do it with applicative.
So if you rewrite this in terms of bind and lambdas, you'll see that every time you create it, you bind a new variable, you make a new name with a lambda. You have X and Y, and you don't use any of them until the end, till the very last thing you're going to apply. That's a good sign that you can do it with applicative instead.
Is there an easy way to see that without having to do it painstakingly myself manually by hand and then they'll pop out? Because like what you're saying there is correct. Obviously, if I rewrite it manually, I'll see it, but
Yeah.
that's a pain. Is there an easy way to see that?
I think you'll quickly get used to it. Just the same way Tony said that we're creating a bunch of local variables and none of them gets used until the very end.
The way that I normally go about it is I start with applicative, and then if I have something content sensitive, I'll go to do notation. Because we're functional programmers, we hate naming stuff, right? So it's better if you use the applicative.
So that you just go the other way around.
Rather than inventing X, Y, and just doing nothing with those names.
Yeah, fair enough. Right, you have the bad habit of using variables when I don't need to.
The answer is yes.
Yes. Yes.
Instead, leave return in monad and give it pure as default implementation.
Nice.
Cool.
Anybody else? Or
I was going to add a comment to your final comment. Only use applicative when necessary because I think you said it makes code easier to read or something. I don't remember what you said.
I said it's easier for other people to use your code.
Yeah,
They don't have to
use it
instance.
because then they don't have to do a monad instance. But there's another point, and that is if you write a function and you only use applicative and the type says that you've only used applicative, then by looking at the type I can determine the constraints on the things that you've done inside that function. So I can immediately look at the type and say you've not done any context sensitive computations inside here without looking any further. So I think that's another benefit of doing everything that you need to do and not anything more than that.
Type says documentation.
Yeah.
Alrighty.
There's a lot to deserving of that.
Thanks, man.
So